Uh, can the students share online? Okay, I'll quickly recap whatever I covered in the last few seconds. When we are talking about molecular simulation, we make use of empirical potentials. Okay, and the most simple example is the Leonard-Jones potential. This is a potential for a pair of interacting atoms. Typically, these are called as non-bonded terms because there is no covalent bond between these two atoms. And you have a repulsive potential where the atoms will repel if they are below the equilibrium separation distance. And whenever they are above the equilibrium separation distance, you will have an attractive quotient. Okay, so this is the attractive component, this is the repulsive component, and somewhere intermediate, at intermediate distances, we have the minimum energy, or this is also called as the equilibrium bond separation distance. Okay, and this is a very nice demo that I am showing. For a bunch of atoms that interact through the Leonard-Jones potential, and this link I will share with you later. But basically, you can see that you can change the kinetic energy of these particles, and you can observe how atoms will rearrange just by using a very simple Leonard-Jones potential, a two-dimensional system. You can also see interesting phenomena like formation of vacancies and other defects. And you can, of course, track the trajectory of these atoms and get various properties like diffusion constants, etc. Okay. Okay, and MD, as you know, is a very versatile technique. It can give you structure property correlations at various length and time scales. And the power behind MD simulations is that you can visualize what is going on at the nanoscale. Right? So typically, when you do experiments, let's say a tensile deformation of some specimen, it's very hard to see what is happening at the nanoscale. Like, you need very powerful, sophisticated analytical instruments to see these things. But with MD, it is much more straightforward. So again, some examples here. So let's say you want to study the tensile deformation of a polyethylene structure. We can observe various mechanisms for melting and recrystallization or formation of cavities, and you can backtrack to how the structure is, right? That is giving you this particular property. If you want to simulate, let's say, polycrystalline aluminum, we can see how the grain boundaries will deform, what are the stresses that are developed, and so on. And the advantage of MD is that you can create very complex structures as well. So for instance, some composite structure here. If you want to see how two different materials with different properties, like silicon and polymer, what sort of mechanical properties do you get, right, because of such a composite structure. All of these you can readily estimate. Okay. There are several examples. I won't go into too many details. But based on your bandwidth in terms of computational resources, you can even do simulations of billions of atoms. You can get very powerful property prediction. For instance, this is a simulation of how cracks will propagate in a silica glass. Right? You can see there is a predefined set of voids here, and these scientists have shown how these voids will coalesce together and lead to a crack propagation eventually. And this is some our work, recent work, where we looked at the diffusivities of various gases in amorphous carbon. Okay, so the structure here you see is completely disordered. There is no long-range order in this structure, but you can see these nice porous features that are formed along different directions. And we were able to track the diffusion constants along different directions. And all of this is possible by using simple molecular dynamics equations. Yeah, absolutely. Yeah, please feel free to stop anytime. Okay. So that's a great question. How to create the structure, right? So all these structures are completely different. So metals are different from polymers. This is amorphous carbon. So you need some method for first creating the structure. Okay. So this structure we created by using a random distribution of carbon atoms in a simulation box, And then we used a reactive potential that can give you this bond formation. So when you quench the gas-like carbon atoms to room temperature, it will neatly self-assemble to form such a disordered carbon or amorphous carbon. So there is a method for doing it. I can share the reference later on if you're interested. And that's a very important question because you need to start from somewhere, right? Your starting structure is the most important part. And then you need to define your interatomic potentials and then do your simulation. Right? So there are different ways for creating different structures. Okay. Usually that itself is an involved work. It needs a lot of careful consideration. Yeah. Anyone else has any questions? Okay. So in our group, we have been working on trying to make some predictions of mechanical behavior, dynamical properties of materials, thermal properties, and chemical reactivity, to name a few. And we've also worked on various types of materials like glasses and alloys, soft composites, polymers, polymer nano composites, amorphous carbon, etc. And some of these materials I will show you in the next few slides. And MD, as you know, is a very robust technique. It was developed way back in 1950s, late 1950s. So, for the last 50, 60 years, it's been growing very rapidly. And people are discovering new materials, developing new potentials for these materials, and also developing new algorithms for simulating these materials. Okay. And I think you already had some introduction to what is the interatomic potential, but just a very brief snapshot of the kind of materials you can simulate, ranging from simple hydrocarbons to very complex molecular crystals, for example, in explosives, battery materials, a very hot area of research right now, biomolecular simulations, let's say DNA and drug delivery and all these things, you can simulate using molecular dynamics. And if you just consider a single force field, okay, this is a well-known reactive potential react effect, you can see that it has parameters for several types of atoms and several types of materials, okay, ranging from hydrocarbons to nitrogen-containing compounds, etc. So are you able to see the screen clearly? These labels are visible to you? No. It's not visible. Okay. Yeah, I think we have to make do with this. I cannot increase the resolution. Okay. All right. So this brings me to the bulk of my talk. So here I will describe how we use molecular dynamics to understand a very interesting property of material called viscoelasticity. Okay. Has anyone heard of this term before? I can see some people nodding heads. So feel free to share whatever you know. As well as elasticity. Absolutely. So this was discovered way back during the times of Newton and Robert Hooke. Robert Hooke, as you all know, he was the one who gave the Spring's law, right? Hooke's law for linear elasticity, which tells you that force is proportional to displacement, right? If you take a spring and you extend it, if you apply a force, the displacement is proportional to the force, right? And Newton is famous for giving the law of viscosity, okay, that governs movement of fluids, any fluids, right? So honey, you know, is very viscous, water is very less viscous. So it all has to do with what are the shear forces in that liquid or in any material. So viscoelasticity is basically a combination of viscous property and elastic property. And the viscous property, if you can imagine, it is something that dissipates energy. Okay, it is dissipative in nature. What that means is, if you take a liquid and you apply a shear stress on this liquid or any deformation, this material will not store the energy. Okay, it will be dissipated usually as heat, right? Whereas if you have elastic materials, highly elastic materials, then let's say you apply a deformation and then remove the deformation, it will come back to its original state. Okay, as long as you are in the elastic regime. So what we say that it stores the energy, stores the elastic energy, right? And whenever we talk about any material, it's always going to have some percentage of viscous and some percentage of elastic component. Okay. Nothing is 100% viscous or 100% elastic. Right? And when we talk about viscoelasticity, there are three important phenomena that people talk about in literature. The first is called stress relaxation, where if you apply a constant strain, then it results in a decrease in stress as a function of time. There is something called a creep. Okay, if you work with materials, this is a common phenomenon that you will encounter. You can imagine, let's say, a suspension bridge where vehicles travel over a period of 10 to 20 years, right? So gradually this bridge will start deforming, okay? And it can lead to catastrophic failure also. So basically, whenever a body is subjected to constant stress, right, the material will undergo a deformation or strain as a function of time. This is called a creep deformation. And what we are interested in is neither of these two. There's a third property called as dynamic modulus. Okay. So imagine a simple stress strain curve. I think all of you would have encountered this in your high school physics. So we have a completely hypothetical elastic material, 100% elasticity. If you start applying the strain, okay, the strain is along the x-axis, the stress is along the y-axis. If you apply a strain and then remove it, okay, or in other words, you load a material and then unload the strain, you're going to see a perfect relationship, a linear relationship between stress and strain. Okay, this is basically Hooke's law. But whenever you have a viscoelastic material, okay, when you load the material and unload it, you're going to see a hysteresis behavior. There'll be an area in the stress strain curve which will have a finite area. Okay? This area corresponds to the amount of energy that is dissipated as viscous heat or viscous losses. Right? So this is what we refer to as dynamic modulus. Whenever you repeatedly apply a load and remove it, the stress and the strain will not be in sync with each other. Okay? And this phenomenon is very important because anywhere you have a cyclic deformation or a continuous deformation, right? If you think of automobile engine, you have the piston continuously undergoing repeated stress strain cycles, right? So that leads to a lot of viscoelastic heat that is generated, and it's important to have materials that do not, show either fully elastic or fully viscous properties. Somewhere intermediate you want it. Okay. Yeah.
For this fluid, you said only viscosity.
Right.
The curve will look like in.
So there's one very important point. It depends on the rate of strain. So this is a time-dependent phenomenon. So for liquid, whenever you deform it at low frequency, small frequency, let's say in the order of hertz, right? You're doing a deformation, one deformation per second. Then it will be highly viscous. But if imagine hypothetically you're doing it at very high strain rates, like several million cycles per second, then it will behave as an elastic material. So even liquid water, if you do a deformation in the terahertz regime, very high frequency, it will behave like an elastic material. So this is highly dependent on the rate of deformation. We discussed that in the next video. So right after Robert Hooke and Isaac Newton developed some basic understanding, people wanted to understand what exactly it is in the material that's causing this viscoelastic nature. So people came up with various models to understand this. Maybe some of you are aware of this. There are what we call as elements of viscoelasticity. Okay. Again, it's very simple. The elastic portion is modeled by means of an ideal spring. This term E here refers to the modulus. Okay. So force is proportional to displacement here. And the viscous component is modeled by using a model called a dashpot. A dashpot is basically a damper used in automobiles typically that will dissipate the energy. Okay. So people were trying to put these two elements in various combinations like series, parallel, or in multiple numbers along series and parallel. And just like you have these resistors and conductors and electrical circuits, you can place them in different ways. People started to develop various models based on these things and dashboards, and they were able to explain some interesting phenomena like creep and stress relaxation. But still it doesn't explain what is happening to the material in the nano scale, okay, that's causing these mechanisms. And this is where our research on using molecular dynamics is very helpful, because we can engineer these materials in some way to give us favorable properties for viscoelasticity. Okay. And before I go there, why is it important? As I mentioned, viscoelasticity is universal. Any material that you take is viscoelastic. And whenever you have functional and structural applications, for example, in an automobile, or an earthquake protection for a building or an aeroplane, basically any structure that undergoes repeated cyclic deformation, right? You need materials that will damp out these vibrations or damp out these cyclic deformation. And here we are talking about materials typically in the order of crystalline composites and alloys and glasses. These are materials which have favorable properties. I'll explain more as we go along. And here we are talking about very high frequency deformation. Okay, the deformation is of the order of terahertz. Okay, tera is 10 to the power 12. So imagine a material undergoing 10 to the power 12 cycles of deformation every second. Okay, that's the kind of frequencies we are dealing with. Of course, in common day-to-day applications, you won't encounter such high frequencies. Right? Typically, these deformations might be in the order of hertz or kilohertz, not in the terahertz. But this is important for certain high-tech applications like nanomechanical resonators or interconnects that people use in computer chips and so on, where it is known that frequency can reach such high values. Okay. All right. So how do we study this? Okay. The method itself is very simple. When we apply an oscillatory deformation, okay. Again, remember that we are applying a cyclic deformation. Okay. In this case, an oscillatory deformation. The theory of viscoelasticity tells us that there is something called as the dynamic shear modulus. Okay. The complex, it's also called as the complex shear modulus, G star, that is made of two terms. Okay, G cos delta and G sin delta, and it is just a mathematical convenience that it is written this way. In fact, there is nothing imaginary or complex about this number. It's just a mathematical convenience. Okay, so what do we do here? So this is the schematic of an oscillatory deformation. So the blue curve that you see is a sinusoidal strain. Okay, imagine a material that's undergoing a sinusoidal strain. And the green curve is the resultant shear stress, right? So the blue curve is the shear strain, denoted as gamma xy, and the green curve is the shear stress, denoted as tau xy. Okay, xy stands to the plane and direction along which it's sheared. Okay. And if you notice carefully, there is a phase difference between the strain and the stress. Okay. So the stress is lagging the strain. This is common for all viscous materials or viscoelastic materials. And the amount of phase difference or phase lag is going to give us how much is the loss modulus or the storage modulus. Okay. So typically delta ranges from 0 to 90 degrees. Okay, 0 degrees means that the strain and the stress are perfectly in sync. Okay. It is something similar to an ideal elastic material that we saw. Whereas any material for any practical application, it will have a finite delta. Okay, so delta of 90 degrees means that the material is purely viscous; it doesn't have any elastic component, and that you can see clearly. Cos 90 will go to 0, whereas sin 90 will go to 1. Right? So it always lies between 0 and 1. And the most interesting thing, as I mentioned, is that the storage and loss modulus depends on the rate of deformation. Okay. So what I've shown here is the variation of storage modulus, the red curve, the loss modulus, which is the green curve, and what we call as the loss tangent, tan delta. Okay. All of them in logarithmic scale as a function of the frequency. Okay. So again, the frequency is important because frequency is the frequency of deformation. Okay. A very small frequency means that it's very slow strain rate deformation. Very high frequency, something like terahertz, is of course a very high strain rate deformation. Right. what is interesting is you have this characteristic frequency where the loss modulus shows a peak. Okay, and we want to operate in such frequencies because that is where maximum damping happens. Okay, we want to enhance the loss modulus because that is how the material can dissipate energy, right? So this frequency response is something of very important consequence for developing these materials. Okay. And one more motivation for, amplitude is again very important. There are two regions in viscoelasticity called as linear viscoelasticity and non-linear viscoelasticity. So when you have small amplitudes, we are in linear viscoelasticity region, which basically means that the strain amplitude is not important. But when you go to very high strain amplitudes, it will depend on the amplitude also. That also we study later on. Typically in the form of heat, it can also dissipate in the form of sound, or if there are some magnetic domains, it can lead to magnetization losses. If there is some electric conduction involved, it can also lead to electric losses. It depends on the material. Yeah, absolutely. Crack formation is also one mechanism of dissipating energy. Yes. So storage modulus, imagine a linear spring, an elastic spring. So whenever you deform it and remove it back, right, it will go back to its original shape. So whatever energy you're putting in the deformation, you're recovering it back. So it's completely conserved, right? But that is just an ideal picture. In principle, no material is perfectly elastic. It will always have some loss of it. Okay, so this is what is called as an Ashby plot. In material science, such a plot measures two properties. For instance, here the stiffness along the y-axis and the loss tangent along the x-axis. And there are various materials that are listed here in this plot. Okay. If you think of materials that are soft in nature, like rubbers or polymers, typically they do not have very high stiffness. They have very low stiffness, but they are very viscous in nature. These polymer chains are very viscous. They can slide past each other. Okay. So they'll have a very high loss tangent. Okay. On the other hand, if you think of alloys and other composites, hard materials, they will have a very high stiffness but very low loss tangent. Okay. But you need both of them to give you a high loss modulus. Okay. So there are some materials but that people have started exploring in the recent past, where you create a composite structure. Okay, composite made of soft materials and hard materials, so that you simultaneously have high stiffness and also high loss tangent. Okay. So this is where we are targeting. We are targeting some composite structures that are made of soft materials and hard materials, right? That will give us both the properties. Okay. So let's go into characterization of viscoelasticity. So as I mentioned, what we are doing is assuming you have a simulation cell that is filled with whatever material you want. We are applying a sinusoidal strain, okay, that is gamma xy. You can see that this is a simple sinusoidal function. The deformation frequency is given as f, right? So higher the f, the faster is your deformation. Okay. And we can measure the resultant shear stress, and the shear stress will have a phase difference delta, as I just mentioned. And by some very simple curve fitting, you can find out what is the storage modulus and loss modulus. Once you find delta, you know what is G, you can find out what is the elastic modulus and the loss modulus. And in simulation, it will look something like this. This is a animation of one of the structures. So you are applying a sinusoidal deformation. Okay. And we looked at various types of composites. The first part of the talk, I will discuss our results on crystalline composites. So you can see two types of materials here. Okay. One is a set of atoms colored in blue. That is a very stiff material, stiff elastic material. And the one shown by the red region, this is a soft matrix. Okay. So we want high viscous and high elastic component, both of them together. That will give us favorable viscoelastic properties. Okay. This is one particular configuration. The other is what is called as a superlattice structure or a sandwich-like structure, where we have alternating regions of stiff and soft materials. Okay, and both these materials, the red and blue, they are crystalline in nature. They are perfectly ordered, face-centered cubic materials. Further, we also looked at the effect of chemical and structural disorder in materials. So this snapshot that we see here is what is called as an ordered alloy. There are two types of atoms again, yellow and blue, that are neatly arranged in a periodic orderly fashion. The one in the middle you see here, there is no chemical order, okay, but there is structural order. It is still following a cubic symmetry, but the atoms are placed randomly in this lattice point. Okay, and the third structure is what we commonly call as glass or amorphous structure, where there is neither chemical order or nor structural order. Okay, and I won't go into the details here. We apply periodic boundary conditions. We simulate few tens of thousands of atoms, and we use lamps for all these simulations. Okay, so let's briefly look at what interesting results we obtained in terms of the crystalline composite. So as I mentioned, we have two types of interactions here, what we call as the stiff interaction and the soft interaction. These are the two materials that I've shown here. The red is the soft phase, the blue atoms are the stiff phase. And the beauty of such a simple model is that we could make use of simple Leonard-Jones terms, okay, for describing these interactions. So the Leonard-Jones that you saw a few slides back, that is all the complexity that we are building into. And to bring in the stiffness contrast, we are artificially increasing the epsilon parameter of the Leonard-Jones term for the stiff phase by 4 times. Okay, so the red atoms have let's say epsilon equal to some value, and the stiff phase, the blue atoms, have 4 times that value. Okay. So by just introducing the stiffness contrast, we can study what effect it has on the viscosity. Okay. And our goal is to see how this nanostructuring, so let's say in terms of the periodic arrangement, what are the effects of sizing or the inclusion size, all these are various ways of nanostructuring the materials, how that will affect the viscoelastic properties of these materials. Okay, so a very quick example of how this heterogeneity in this material will affect viscoelasticity. This is the stress and strain response for 3 different systems. On the left panel, you see a pure soft phase. All the atoms are red in color. On the rightmost panel, you see a pure stiff phase. Okay, so this material has 4 times the stiffness of soft phase, and somewhere in between we have a composite structure. Okay, the stiff inclusion is present in a soft matrix. Okay, and clearly you can see that whenever the material is homogeneous, okay, the leftmost panel and the rightmost panel, we see that the phase difference is almost 0. Okay, it shows that there is no heterogeneity in the deformation. And these materials are highly elastic in nature, which is something according to what we expect, because we know that metals are highly elastic. The phase difference is typically very low. Okay, that is a consistent result. And the moment we introduce a composite structure, we see that there is a finite phase difference, about 22 degrees. Okay, and as a result, if you look at the loss modulus value, this is about 60 MPa, this is close to 0 MPa. And the composite structure shows, 2 orders of magnitude larger loss modulus compared to the pure soft phase. Okay. And now comes the most important thing. How does this depend on the frequency? Right. So we saw that whenever there is a characteristic frequency, we do expect a very high loss modulus, and we do see this for various system sizes, starting from 7 unit cells along each axis of the cube, all the way up to 21 units. We are just replicating the structure along all the 3 directions. This is a 3-dimensional simulation. And we see that whenever we are in this high frequency range, somewhere in the order of terahertz, okay, we see a rapid enhancement in the loss modulus for the composite structure. Right? This is something interesting. We don't know what is the mechanism behind it. Okay? That is what we are interested in probing. And when you go to lower frequency, the loss modulus actually goes down to zero, which is again what we expect, because elastic materials should show very less loss modulus. It should have a very high elastic modulus or storage modulus. Okay. So any material, provided you go to a characteristic frequency, can show you a very high loss modulus. Okay. This is something that's established in the literature of physical elasticity. Okay. So the clue that came to our mind is that how many of you have heard of phonons? Yeah, everybody has heard of phonons. So these are lattice vibrations. They're responsible for transferring heat or sound in materials. And whenever you have a high frequency perturbation, the waves will transfer through the phonon mode. Okay, and it is known that such structures will have phonons. These are vibrations. These vibrations are in the order of terahertz. Okay, so that's the first clue that we get. Okay, somehow the phonons are responsible for affecting the viscoelastic properties of these materials. And this is more so because our structure doesn't have any defects. Yeah. Size of structure doesn't matter here. So you can use any simulation cell size. So there are two answers to this. One thing is, in MD we cannot go to hertz or kilohertz because it will be very long simulation. We might need maybe 10 to the power 12 simulation steps. This is not possible. And the other thing is, we wanted to study high frequency dissipation. So we are deliberately choosing frequencies in the range of few gigahertz to terahertz. So this is in the log scale. Okay. So in our structure, we do not have any other defects. As you mentioned, crack propagation is one mechanism for damping. So we don't have any defects in our structure. So this clearly tells that the phonons are responsible for dissipating the energy, and there is a theory for how these phonons will dissipate in an anharmonic fashion. I'll come to that later. And the way we can characterize it is by measuring a property called as the Grunheisen parameter. Okay. So I won't go into the math too much, but very briefly, what we do is this omega that we see here, okay, omega I, is the frequency of one particular phonon in your system. Okay, and there are multiple such phonons in any system. What this Grunheisen parameter measures is that whenever you have a small and elastic deformation, okay, because of which you're changing the volume, delta V, these phonon modes are going to change. They will either become higher or lower. Okay, and the rate of change of phonon modes with respect to volume will give us what's the anharmonicity of these phonons, right? And this is the quantity that you can compute for any material, any elastic material. And we computed that for the homogeneous materials. Okay, the red curve is for the pure soft phase. The blue curve is for the pure stiff phase. So both of these are homogeneous. And the green one is for the composite structure, okay, with a phase fraction of 47% of the stiff inclusion. And we can clearly see that there are some phonon modes, okay, that have a very high Grunheisen parameter. Means that the phonons are somehow getting affected because of the deformation, and the way they couple with each other is going to give us the anharmonic damping that we are observing in the results. Okay. And one more interesting thing we saw was whenever we have an inclusion, okay, this is the stiff inclusion in a soft matrix, we saw that the soft component was getting deformed much more than when when there was no deformation in the system. Okay, so when you are applying an oscillatory deformation, the soft material is basically undergoing selective deformation. Maximum deformation is carried out by the soft material, and these which have high Grunheisen parameters, these are coming from the soft phase. Okay, and the stiff phase has much higher frequency. because stiff materials will have higher frequencies. And this clearly gives us a structure property correlation between the soft inclusion and how the phonons in the soft matrix is giving us excitation of these phonons. Okay? That is directly responsible for the loss modulus. Okay. And what is interesting is we already saw that when you have pure components, okay, we observe very less deformation. Whenever you're creating a composite, we have very high deformation. And what this measures is the loss modulus as a function of volume fraction of a stiff phase. Stiff phase is an inclusion inside the soft matrix. And volume fraction equal to 0 means that it's pure soft matrix. Volume fraction equal to 1 means that it's pure stiff matrix, okay, pure stiff phase. And naturally the loss moduli are 0 at either end. But whenever we have an inclusion, we see that the loss modulus is getting enhanced. Okay? And this value is actually 20 times larger than the loss modulus of predicted values. So when you think of classical prediction based on some composite theory, there are some bounds that you can predict for the composite modulus. And these are the upper and lower bounds that classical theory predicts. Okay? Whereas our simulation results are giving us 20 times larger moduli. Okay? This is something that people have not observed in literature before. And the reason is because of the phonons in the system. Okay. And now the effect of simulation cell size. I think Dr. Dowell, what you asked. What we're doing here is we are fixing the stiffness fraction. Okay, this is fixed at I think 47% of the stiff phase. And what we're doing is we're just changing the size of our simulation cell, okay, from L equal to 7 all the way up to L equal to 25 units. And as we do that, we see that the curve is getting shifted to the left progressively. Okay, so from bottom to top, the inclusion size is increasing, okay, while maintaining the same volume fraction. And you don't have to worry about these numbers; they are just tagged for clarity. But the interesting thing is that the frequency goes to lower and lower values. Right? This clearly tells us that when you have different nanostructuring effects in your material, you can fine-tune the frequency at which the loss modulus is enhanced. Okay. Now this gives us a link actually. We are telling that if the phonon modes are responsible for dissipation. Okay, phonons are lattice vibrations. And if you have a very simple idea about frequency and then the speed of sound or speed of sound propagation of these materials, we'll see that if you plot the loss frequency, which are these values, okay, the peak loss frequency, as a function of inverse simulation cell length, okay, we see a straight line. Okay, and again, there is nothing surprising about it, because if you look at the dimensional analysis for the slope, okay, this is frequency divided by 1 over cell length. This will give us a unit of meters per second or velocity. Okay, frequency is 1 divided by time, and 1 divided by simulation cell is 1 over meter. So when you take a slope, you will get units of velocity. Okay. And this slope comes out to be a reasonably high value, 1400 meters per second. And this was seen to correspond almost exactly with the speed of sound in these composites. Okay. So this gives us one more direct evidence that the phonons that are responsible for sound wave propagation are the ones that are responsible for the peak damping in these materials. Okay. So such correlations can come only when you look at the material behavior at the nanoscale. Okay. And the other important finding, of course, is that based on the inclusion size, you can have viscoelastic damping at various frequencies. Okay. So imagine you want to damp out vibrations of a particular frequency range. You can choose a specific set of inclusion size for such an application. And very briefly, we observed a very similar thing in the superlattice structures as well. So these are the sandwich kind of structures. And here again, we saw that when we increase the spacing between the stiff and the soft phase, the frequencies are going to the left. But what's interesting is there are two peaks that are now observed. One is for the standard crystal effect. At some frequencies you have high damping. The other is coming from the periodicity of the structure. Depending on what is the periodic spacing, we get a second peak, right? So again, if you do a similar analysis, when we take the peak damping frequency and we plot it as a function of inverse simulation cell size, we get two slopes here. Okay, the two slopes are different, and these slopes again, when we verify, they correspond to the longitudinal and transverse transverse vibration modes of this material. Okay, we all know that the sound waves have longitudinal and transverse modes, and these sound waves directly correspond to these slopes. Okay, so we were very happy with this result. So we wanted to extend it further to see the effect of ordering in our system. But before I go there, any questions or clarification? Okay, all right. So what we did was to see the effect of chemical order and structural order. Okay, so we have what's called as an ordered alloy, a random alloy, and a glass alloy. Again, all of these are modeled with a very simple Lennard-Jones potential. And using the same potential, we can observe three different phases. Okay? That's the power behind using a simple potential. And we do the same oscillatory deformation to understand the damping in all the three materials. And this is a representative figure for the stress-strain relation between an ordered structure, a random structure, and a glass structure. So we see that the ordered and random structures show very little phase deformation, phase lag, whereas the glass structure showed a much larger phase. Okay. So we wanted to look at the effect further. So we first did this frequency speed simulation, as I mentioned in the past few slides, where we look at the loss modulus as a function of frequency. And what's interesting is the ordered and random alloys, which are structurally ordered, right? There is no structural disorder in these two alloys. They show a loss modulus that is going to zero at low frequency. Okay? But the glass alloy, the glass structure, shows a finite loss modulus even at very low frequency. Okay? This is something that was completely out of our expectation. Okay? Why is that the case, right? And the other thing, of course, is the ordered alloy shows much less loss modulus compared to the random alloy, which is again much smaller compared to the glassy alloy. Okay? So glassy structures are something that gives you very high loss modulus, not just at the peak frequency, but also at lower frequency. The other interesting thing is the rate at which they go to zero at low frequency. So the ordered and random alloys, they show a power law behavior. This is the same data for loss modulus as a frequency plotted in a log scale. You see that it's going down to zero in a power law fashion. Okay? Whereas the glass alloy clearly shows that it doesn't go down to zero. Okay. So why is that the case? Okay. So the first thing we wanted to find out is what is the mechanism of the high frequency range. I won't go into details here, but what we did was we found out the range of frequencies in these materials for ordered, random, and glassy structures. And we saw that whenever we impose a deformation at a particular frequency, let's say 1.4 terahertz in the top figure or 3.85 terahertz in the bottom figure, okay, some two frequencies that we picked up from this range, we see that the phonon modes that are closest to those frequencies are cited. So their temperatures, the y-axis is basically the temperature of the phonon mode. There is a way to calculate it from our ND simulation. We see that those phonon modes are excited. Basically, the energy is going into those phonon modes, okay? And they are the ones responsible for damping at that particular frequency. Okay? So we could clearly show that the phonon modes are excited. That is at the high frequency, and in the low frequency, okay, we saw that the glass structure has finite loss modulus. It doesn't go down to zero. So again, here is where visualization in molecular simulation is extremely powerful. Because when you run a simulation, all you see is a bunch of data. Right? By seeing the data, you won't be able to understand what's going on. But you can visualize the trajectory, right, of all the atoms during your simulation. And when we do that, we saw that the glass structure shows what are called as soft spots. Okay? This is well-known phenomena in deformation of glasses. The interesting thing here is, if you consider a perfect crystalline structure, okay, all the atoms are occupying the lattice position, and these atoms cannot occupy any other position. Okay. They can diffuse to other lattice points, let's say, but they cannot occupy typically some interstitials or voids in the structure. Okay. Whereas the glass structure doesn't have any long range or short range. It has short range order, but no long range order. Okay. There is no periodic arrangement of that. So what this means is there is a lot of free space for these glass atoms to move during our simulation. Okay. And all these atoms that I have shown here with various color codes, these are atoms that have diffused during the simulation. Okay. And we can see small pockets of atoms that have diffused together. Okay. These are what are called as soft spots. Right. So this contributes to an additional channel for damping. Just like how we have phonon-based damping at high frequency, these are much lower frequencies compared to terahertz. Right? So 45 gigahertz is over here. This is 4.5 gigahertz, and this is 4.5, and this is 0.45. Okay. Two orders of magnitude difference for these three structures. And we see that when you have lower and lower frequencies, you are enhancing the formation of these soft spots more and more. And this is directly contributing to additional mechanism of damping only for the glass structure. Whereas this is absent for our crystalline structures. They cannot diffuse into empty regions. Right? So these are some very powerful correlations that we could get by running some MD simulations. And the next logical step that we wanted to go was, there are different types of glasses. Okay? That people commonly study. You can have effect of composition. So let's say you just have a single component versus two or more components. You can have bulk metallic glasses. Silica is one common example. So all these glasses have different thermomechanical properties. They have different gas transition temperatures, different stiffness, different interactions. So we wanted to see if the mechanism for viscoelasticity that we observe, is it universal for glasses? Okay. Because ordered structure is just ordered structure. You cannot have multiple types of ordered structure. Whereas in glasses, you can have a lot of complexity. Okay. And we did the same thing for all these glass structures. What I've showed here is the loss modulus as a function of frequency. And we saw that all these glasses showed a high frequency peak, just like our original Leonard-Jones glass. And all these glasses also showed consistent loss modulus at low frequency. Okay, they did not go down to zero. We are all finite values here. Okay. And these mechanisms we did explore in these glasses also, and they also led to the formation of soft spots and the high frequencies. The vibrational mode got excited and so on. So we are able to see a clear trend between the glass structure and the viscoelastic properties that we could observe. Okay, so the next part of the result, we wanted to extend it to soft matter. Okay, so far we have dealt with hard inorganic materials. These are alloys and glasses. But what about polymer composites? Okay, these are typically candidate materials for high viscoelastic loss. Okay, because the polymer chains are soft in nature, they can dissipate energy, and we wanted to extend it to polymer materials. Okay. And the first example that we looked at was Nano Composite, where we have two different configurations. Okay. The first configuration is shown here. The red colored sphere that you see is a nanoparticle, and the blue atoms are one type of polymer chain that has much higher stiffness. compared to the yellow atoms here. Okay, that's the matrix. These are again polymer systems here. So there are two types of polymer chains, one with high stiffness and one with low stiffness, and there is a nanoparticle in the center. Okay, and this is the first configuration, which we call as the collapsed configuration. Okay, the high stiffness chains are collapsed on the nanoparticle, and the second configuration is what is called as the stretched configuration. Okay, so imagine you heat up this nano composite. The blue polymer chains have enough kinetic energy to stretch out, right, and experience the configuration with this. Let's say you have these two configurations, okay, and we again subjected this to the oscillatory deformation, and this time we are looking at the storage modulus instead of the loss modulus, and we can clearly see different trends for these three different structures. Okay, the one shown by the green curve, the green markers. This is for a simple polymer system, homogeneous polymer, that is not very stiff. We expect that, right? Soft polymer doesn't have a very high storage modulus. Whereas if you insert a nanoparticle that's in a collapsed configuration, we see an enhancement in the storage modulus. Okay, because now the nanoparticle can also take some stress, and it becomes stiffer because of the inclusion. But what is exciting is if you have a configuration where the stiff chains are further stretched out, it is giving us an even larger enhancement in the storage modulus. Okay, and this is because now the polymer chains can interact with themselves, the stiff chains can interact with the soft chain, and because of the restriction to the motion, it is going to give you higher stiffness, okay, or higher elastic modulus. We went on to show that you don't even need to have a nano composite. Okay, you don't even need to have a nanoparticle in the material. Even a binary mixture of polymer blend, okay, that has a stiff polymer and a soft polymer with two different configurations, right? What is called as a collapsed and expanded configuration or stretched configuration. That can also give rise to very interesting mechanical property enhancements. About 3 to 4 times larger storage modulus in one particular configuration compared to the other. And we were able to look at the mean square displacements of these polymer chains and explain our data based on the diffusion constant. I think you already had some tutorial on mean square displacements and diffusion constant. So these are very powerful structure property correlations that you can get by running these molecular simulations. Okay. And I'll just take maybe 5-10 minutes, is that okay, to wrap up this portion of the talk. These are some recent results that we have done with one of my PhD students. And here we want to mimic some structures that are found in nature. Okay. Why is that? Because nature has several materials that show extremely good properties, just because of the billions of years of evolution, right? Organisms have evolved so much that some of these structures have superior mechanical properties that even we are not able to match by artificially synthesizing these materials. Okay, our bone and teeth are some examples. Here they have very high strength, right? And there's another material called nacre. It's also referred to as mother of pearl. It's basically a lining that's found in the oyster shell. Okay? Oysters are organisms that contain pearls deep in the ocean, and this layer gives it a protective coating. Okay? And the interesting thing is it is made of a mineral called aragonite. This is calcium carbonate. Okay, it's a highly stiff material. It's an inorganic material, and naturally inorganic materials are very brittle in nature. They can break. But this material also has a small fraction of a protein base. These are small proteins, and these proteins are basically the ones that hold together these minerals together. Okay, so the schematic here, I'm not sure how many of you can see it. These are small grains, typically of the order of 30 to 50 nanometers. These are aragonite grains, and the polymer phase acts as a glue to hold together these inorganic states. Okay, overall it looks something like this, and this structure is what is called as hierarchical structure. Okay, So these grains can arrange together in neatly repeating fashion, and you get a tablet. Okay? This is about 5 to 10 micrometer wide, and these tablets can further arrange, okay, in a periodic repeat unit to give us the final structure of an acre. So this is called as a brick and mortar arrangement. Don't go into the details here. But because of such an arrangement, we have very high toughness. So imagine you are subjecting this structure to a very high strain rate deformation. Okay? It can dissipate energy very efficiently. It will not crack under such a high strain rate deformation. Okay? And we want to mimic such a property by using our MD simulation. So we built some coarse-grained models. So the ones that you see with the pink colored atoms, these are representing the mineral phase, which is high stiff material, and the yellow colored atoms you see are the polymeric phase, the soft material. Okay, and we again looked at two different configurations. One is sort of a polycrystalline arrangement where you do not have any repeated ordering in your mineral phase. The other is where the small cubes, all of these are small cubes of the mineral phase, they are arranged in a cubic fashion, and the polymer chain is surrounding these individual grains. Okay, and the potential is slightly different here. We use what is called as the leaf spring model. This is one of the tutorials that we will cover later on. Basically, it has two terms, one of which is the standard Lennard-Jones potential that you're familiar with. The other term is what is called as the Feeney potential. This is basically a bonded interaction because the polymer chains need to be bonded with respect to each other. Okay? All the atoms in the polymer are bonded. And this is basically coming from the bonded interaction. Okay? So it has non-bonded and bonded interaction. Okay, so the first thing we looked at was the tensile behavior of these two structures. We are just applying a tensile load along the x-axis for the two structures, and clearly we can see that the mechanism of deformation is completely different for the two cases. In one case, the mineral phase is sticking together, and the polymer chains are stretched from the interfacial interaction. The other case, the minerals are completely taken apart, and whatever interfacial polymers are there, they are getting stretched here. Okay, and this we can see directly affecting the mechanical properties. This is the stress strain curve for the ordered structure and the staggered structure. And it's also showing different Young's moduli as a function of interaction strength and so on. So all this contrast is coming just because of the way these composites are arranged. We also did similar viscoelastic properties of these composites by applying an oscillatory deformation. And here again, we could see that the storage and loss moduli are completely different for the two structures. Okay? It depends whether these mineral phases are ordered or completely staggered. What is the time? Can I take 5 more minutes? Okay. All right. The final example that I wanted to show is a very high strain rate deformation. Yeah.
So now in this the deformation will be stored.
Yeah. It can do that. Yeah. It can do that. So the morphological changes will definitely happen. So here you can see the grains are sheared along different directions, and the polymer morphology will also change. But overall, we are looking at a bulk effect. We are not looking at this as a function of time. The important thing is this oscillatory deformation we are doing over several cycles, typically hundreds of cycles, and we are taking an average property from this.
In this particular case, we are applying force on to the uppermost layer.
Uppermost layer, yeah. We are just shearing the top surface in an oscillatory manner. That is the way we apply an oscillatory load. Because this is cyclic loading, right? This is dynamic modulus. The stress and the strain that we, yeah. So the stress strain relation that I have shown, this is not over just one cycle of deformation. We repeat this deformation over hundreds of cycles, and we take an average stress and average strain. And this deformation is because of the cyclic nature of the input. Okay, so the final example is a very interesting thing. Whenever you have a high velocity impact, for instance, a bullet or a missile penetrating an armor, right? We have what are called as shock waves that are generated. Even if you have some explosives that are detonating, there are shock waves that are generated in the material. Okay, and there's a lot of research going on in terms of having favorable material properties so that the shock wave can be dissipated. So these are some examples that I'm showing. This is still a work in progress. What happens is we set up a shock wave at one end of the simulation cell. And this is a simple example of aluminum, okay, modeled as Leonard-Jones particles. And the shock wave basically passes from left to right. Okay. And when it does so, it leads to a shock front. Okay. This is the velocity of the wave propagation, and we contrast that with the velocity of the piston that is imparting the shock. And somewhere there will be a drop in the velocity. So these atoms have been subjected to shock, and all these atoms have not yet been subjected to the shock. Okay? And as we keep progressing, the shock wave will move from left to right. Okay? And the precise nature of this curve, okay, if it is very sharp or very diffuse, that will determine how much shock this material can sustain. Okay? And what's also interesting is that when the shock wave progresses, the temperature of that shock region will be very high, typically in the order of 2000 Kelvin. Okay? And we need materials that can sustain such high temperatures. I won't go into the math here for lack of time, but some results that we are currently working on, we are seeing that the structure of the material, of course, plays a very important role in the shock wave deformation. The top structure is single crystal aluminum, whereas the bottom structure is polycrystalline aluminum, basically aluminum with various grains oriented in different directions. And we can see that the mechanism of dissipation of the shock wave is completely different here. Okay? There are these nicely formed grain boundaries in your polycrystalline structure that can give you much higher shear stresses that material can sustain compared to the single crystal aluminum. And finally, we again go back to our nano composite. This example is a system comprised of polyethylene and graphene. Graphene as your two-dimensional pillar. The simulation on the left shows a homogeneous polyethylene system, whereas the one on the right shows a polyethylene with multiple graphene sheets introduced inside. And again, we see that these graphene sheets will take a lot of load, okay, the shock load that you impart to the material. And we can see clearly an enhancement in damping, although not much, about 12 to 13% higher damping when you have a composite structure. Okay. We are still working on trying to understand what is the precise mechanism by which graphene is able to take higher load. But again, this is just an illustration to show that you can have very complex materials and study very complex phenomena by using modular simulation. And by visualizing the structure and calculating properties of your system under various conditions, you can get a lot of interesting and insightful relations between them. Okay? And hopefully you can tailor these materials or engineer these materials for favorable properties. Okay? So with that, I'll conclude this portion of the talk. Any questions you have? Explain the shock wave. Okay. Shock? Shock Sugionio. Okay. Okay. So basically, you have something called as a piston, and this piston will impart a high velocity to your material. Okay, and what we typically monitor is the shock region where the shock wave has already passed versus the unshocked region. Okay, and naturally the shock region will undergo deformation, whereas the unshocked deformation will have different properties. So the pressure, temperature, and density of the shock region will be different. And Sugionio relation is basically an equation of states that tells you how the pressure, density, and temperature will vary as a function of your piston velocity. These are the relations that will describe the property. And typically people measure this as the pressure as a function of shock wave velocity, and there will be a characteristic dependence between these two quantities. So different materials will have different Hookean curves. Okay. And again, the area under the curve will tell you how much dissipation is happening. Yeah. Okay. Any other questions? Yes. Yeah. Okay. These are all classical MD simulations. All of them are classical. These are all classical MD simulations. Phonons. What is your question? What is your question? Projection parameters again from classical MD. Yeah. So what the theory tells you is, if you have n atoms in your system, you'll have 3 n phonon modes. Okay, each phonon mode will come from multiple atoms that are participating, and it's basically an eigenvalue system. Just like you have Schrodinger's equation, right? X I is equal to E psi. This is basically an eigenvalue system for finding the natural frequencies of your system. These are the phonon frequencies. All you need to know is what is the intraatomic potential and what are the atom positions. Okay, and once you impart small deformation delta V, you can find out how the phonon frequencies are changing, and then you can find the Brunelson parameter. Because each phonon mode will have a different Brunelson parameter. Okay. Any other questions?
How do we form a class? Is it required that know the structure of the
Okay, that's a great question.